Hello and welcome back. Today we'll be doing question 3 from the 2010 Step Paper 3. This is a question about primitive roots of unity. So, let's get started. Question 3. For any given positive integer n, a number a, which may be complex, is said to be a primitive nth root of unity if a to the n is equal to 1, and there is no integer m such that 0 is less than m is less than n, and a to the m is equal to 1. Write down the two primitive fourth roots of unity. Let Cn of x be the polynomial such that the roots of the equation Cn of x equals 0 are the primitive nth roots of unity. The coefficient of the highest power of x is 1, and the equation has no repeated roots. Show that C4 of x is equal to x squared plus 1. Part 1. Find C1 of x, C2 of x, C3 of x, C5 of x, and C6 of x, giving your answers as unfactorized polynomials. Part 2. Find the value of n for which Cn of x is equal to x to the 4 plus 1. Given that p is prime, find an expression for Cp of x, giving your answer as an unfactorized polynomial. Part 4. Prove that there are no positive integers q, r, and s, such that cq of x is equivalent to cr of x multiplied by cs of x. Pause the video now to have a think, and once you're ready, restart to see if you were correct. Let's get started with the question. So here, we'll write down firstly the fourth roots of unity. They are 1, I, -1, and -I. We'll notice that 1 is not a primitive root of unity because 1 to the power of 1 is equal to 1. We'll also notice that -1 is also not a primitive root of unity because -1 to the 2 is equal to 1. However, we will notice now that I and -I are in fact primitive roots of unity because I to the 1, 2, and 3 are not equal to 1. Similarly, -I all to the power of 1, 2, and 3 are not equal to 1. Therefore, we can write C4 of x as x minus I multiplied by x plus I, and this expands and simplifies to give x squared plus 1, as required. Now, before we move on to the numbered parts, I will quickly write down all the primitive nth roots of unity for n equals 1, 2, 3, 5, and 6 here in this table. We can now move on to part 1. Here, I'll write down C1 of x and C2 of x, and these are x minus 1 and x plus 1 respectively. Now, we'll move on to C3 of x. Here, we'll write this down in factorized form with each factor being x minus 1 of the primitive nth roots of unity. Expanding and then simplifying gives x squared plus x plus 1, and similarly, for C5 of x, this gives x to the 4 plus x cubed plus x squared plus x plus 1. Using this method once more, we get C6 of x is equal to x squared, take x plus 1. Now we'll move on to part 2. Here we have x to the 4 is equal to -1, and therefore x to the 8 is equal to 1. There are, in fact, 4 primitive eighth roots of unity, and therefore we have n equals 8. Now we can move on to part 3. There are two methods of solving this question. The first method is by directly using Fermat's Little theorem, which is a topic covered in OCR Additional Pure or Edexcel Decision Maths 2. Let's first do method 1. Using Fermat's Little theorem, we have that Cp of x will be equal to x minus 1 Using Cp of x, we have that the complex number, using Fermat's Little theorem directly, we have that all complex numbers of the form e to the 2k pi I over p are primitive roots of unity, and therefore the factors of Cp of x are equal to x take away 1 e to the 2k pi I over p. Expanding and simplifying this will give that Cp of x is equal to x to the p plus x to the p minus 1 all the way to x plus 1. Now let's move on to the second method. Here we will rearrange to get x to the p take away 1 is equal to 0. And then we will factorize to get x minus 1, x to the p plus x to the p minus 1 plus all the way to plus x plus 1 is equal to 0. Since x equals 1 is not a primitive root of unity, we have that Cp of x is equal to x to the p plus x to the p minus 1 plus all the way to plus x plus 1. Now we'll move on to part 4. Firstly, we'll say that no root of Cu of x is also a root of Cv of x, for u is not equal to v. This follows directly from the definitions above. Without loss of generality, if u is less than v, then there does not exist a u such that a to the u is equal to a to the v is equal to 1. Therefore, if Cq of x is equivalent to Cr of x, Cs of x, and Cq of x is equal to 0, then 1 of Cr of x and Cs of x is equal to 0, meaning that either S equals Q or R equals Q respectively, a contradiction to the above, and therefore there does not exist a set of 3 distinct positive integers Q, R, and S such that Cq of x is equivalent to Cr of x multiplied by Cs of x as required. If you liked our video, please like and subscribe, and we'll see you next time for some more fun maths problems. Thanks for watching and goodbye.